Good day, ladies and gentlemen. Welcome back to Chemistry with Mr. Dang here. Today's lesson, we will talk about valence electrons. By now, you should have a couple of things down. The first thing you should have is electron configurations. Electron configurations down. And in this electron configurations, you should know about the noble gas configuration as well. Noble gas configurations. And you should know about protons, neutrons, electrons from the past, okay? And so different things about the properties of an element, the number of protons, the number of neutrons, the number of electrons. Which one of these determine what element it is? Okay? Proton determines the element, determines what element it is. Okay, determines the element. Because that is equal to the that is also equal to the atomic number. Okay, and neutron, it plays a role in the mass of that element, the mass of that isotope. Okay, and electrons, what do? Electrons are involved in bonding. Okay, in bonding, in exchanging. It could be transferred, it could be shared, and you will learn that it could be transferred or shared. Transferred, is that 2 R's? Or shared. Okay, transferred or shared. So it can either be, either gained or lost here. So if it's transferred or shared, it could be gained or lost. Gained or lost. Lost. There you go. That's the right tense. It could be gained or lost. Okay. The electron is the only number that can change in terms of sharing. Okay. Neutrons can change for the same element to have a different isotope. However, there's one number that cannot change for that element, and that number is the proton. The proton cannot change because that determines the element. If you change the number of protons, you will have a completely new element. So neutrons can change to give you a different isotope. Electrons can change because it can gain or lose in a bond, in sharing or donating or taking up electrons. It can do that as well. Okay, and so today we will focus on these electrons called valence electrons, and these are the electrons responsible for gaining, losing, sharing, and all that combines to one word, which is bonding. Okay, valence electrons are responsible for bonding. And what are valence electrons? So valence electrons are electrons on the valence electrons. Let me write this down. Valence electrons are electrons commonly known as electrons on the outermost, that should have been one word, I don't know, outermost, not shell, but energy level. Commonly known as the shell, outermost shell, okay? Electrons on the outermost shell. So if you remember the Bohr model is not completely accurate. It's not accurate in terms of how the atom looks like, but it gives us a good idea about how these valence electrons are located. Okay, so we have an atom that looks like this. If you remember in the past, okay, the first ring, so the nucleus in the middle right there, the first ring can hold 2 electrons. The second ring can hold 8. The third can hold 8. The fourth can hold 18. And the next one can hold, I don't remember. Let me look at the periodic table. Let's go. 2, 8, 8, 18. 18 again. And the next one we add 32, and then 32 and 32. Okay? So 1, 2, 3, 4, 5, 6, 7. Yeah, that's about right. So that's how many electrons it can hold. And we know that it's nice that the periodic table is arranged that way. Because if you look at the periodic table, it looks like this. Okay, look, there's how many elements on the first row. there are only 2 elements on the first row. How many elements are there on the second row? It's element 3 through 10, so there's 2 to 10, so there's 8. Okay. The third row, there's 8, so 2, 8, 8. The fourth row, there are 18. Sorry, let me zoom out a little more. Okay, 2, 8, 18. And then the next one here is another 18. That's how I knew. Okay, I don't remember. That's why I said I don't remember this stuff until I look at the periodic table. And 6th row, notice this is 2. And then this goes with the row 6 as well, down here, the lanthanide series. And then you have that one plus 10 more, that's 32. And row 7 is the same, 32. Okay. And so when we fill in the electrons on the Bohr model to help us with the valence electrons, so keeping that in mind, let's look at a couple elements. Let's say element number hydrogen. Hydrogen only got 1 electron, so there you go. Protons in the middle. Okay. Then we go to lithium, down 1 row. Lithium is element number 3, so it's just H, which atomic number is 1. 1 electron. Okay. Lithium, 3 electrons. You put those here, 1, 2, and then that ring is full. We need to add another ring. And notice it has 1 on the outer shell as well. Okay. If we go over to beryllium, no, not beryllium, but helium. Helium, it's got 2 electrons. We go 1, 2. Okay. And that's a full shell. That's why helium is a noble gas. Noble gas. They have full shell. Okay. All the other noble gas have 8 on the outer shell except for helium because it's only got 2 electrons, and it only takes 2 electrons to fill the innermost energy level. Okay. And you go down to beryllium, Be, it's got 4 electrons, so then the inner shell is full, 1, 2. And then the next shell, 1, 2 more. They want to be as far away from each other as possible. That's why you often see they're on opposite sides. Okay, because electrons are both negative. They want to be as far from each other as possible. Like in real life, we don't want 2 negative people together. That's a disaster. Okay, so 2 valence electrons here. 2 valence electrons. Helium, 2 valence electrons as well. So I'll do a couple more. Hop over to carbon. Carbon. Carbon, column 14. Go to column 14. So carbon, right? It's got 6 electrons. So how do we know? Just a quick review here. How do we know carbon has 6 valence electrons? There's carbon right there. Its atomic number, number 6, right there, tells us there's 6 protons, and in a neutral atom it will have 6 electrons as well. Okay, so the first ring can only hold 2, so you put 2 dots there, positive nucleus in the middle. So 1, 2, that's full. Then we need 4 more, so we need to add another ring. 1, 2, 3, 4. So carbon has 4 valence electrons. Okay. Let's move over to nitrogen. Nitrogen has 7 electrons. So then 2 goes in the middle to the smaller one. And then 5 will go on the outer one. Okay? So then that has 5 valence electrons. Okay? So again, it's 2 in the innermost. 8, 8, 18, 32, 32. And that helps us figure out how many valence electrons. Okay? Another way is you just look at the column. So everything in this first column here will have 1 valence electron. If you don't believe me, you can draw the the Bohr model, and you'll find that it is true. Everything in the second column, will have 2 valence electrons. Okay, you can mark this on your own periodic table to have all this ready, so that when you just look at it, oh, that's in column 2, 2 valence electrons. The transition metals, though, they have multiple valence electrons for each, so there's no specific rule for these. Okay, they're either going to be given to you, or there's a couple that is always 1 or 2, but we're going to skip over this for our purpose in this unit. Okay, and the 13th column here, 13, guys, 13, there's 3 valence electrons. Okay, group 13, 14, 15, 16, 17, and 18. You can drop that 1 in the front. 13 becomes a 3. 14 becomes a 4. This is 4 valence electrons here. 4 valence electrons for that. Group 15, what do you think now? Drop the 1 in the front. It'll tell you 15. And that's what this little numbers at the bottom, that A, 4, 3A, 4A, 5A, 6A, 7A, 8A. There's 1A, 2A over here as well. That's what those A's are telling you. These are your representative elements. Sometimes they're known as the main group elements. Okay, and that number, that A, tells you how many valence electrons. So 6 valence electrons for column 16, 7 valence electrons, and 8 valence electron only applies to everything underneath helium, 8 valence electrons. Because I mentioned helium earlier, it only needs 2 valence electrons to be full. Okay, so that's how you figure out the valence electrons. One more way to figure out the valence electron is from the electron configurations. So valence electrons from electron configuration. What does that mean? This means that from your electron configuration, you can figure out the valence electron by looking at, so look at the highest level S and P orbitals, and then add them together. Highest level S plus P orbitals. Okay, here's an example. Nitrogen. Okay, 7 electrons. I'm sorry, 7 electrons. Okay, write down the configuration: 1s2, 2s2, 2p3. Okay, the highest level S and P. What's the highest level here? What's the highest energy level? Its highest energy level is 2. Okay, look at only the S and the P, and then add those electrons together. You have 2 electron plus 3 electron. That's 5 valence electrons. Okay, so to get the valence electron from electron configurations, look at the highest level and add the S and P electrons together. Okay, so you add the electrons together. Okay, and remember, what's the maximum number of valence electrons an atom will have? An atom will have at maximum 8 valence electrons. Okay, no more than 8. So we go back. Let's do another one of these. Let's look at bromine, for example. Br 53. Oh, 35. That's good. Oh, it would have been a lot of work. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Right? Does that add up to 35? I'll do that real quick, assuming you already know how to do this. So 2, 10, 12, 18, 20, 30, 35. Perfect. So the rule is, look at the highest energy level. What's the highest energy level here? Level 4. So all the 4s. Okay? And then only add the S and the P together. So there's 2 electron plus 5 electrons. So then you add them together, it becomes 7 valence electrons. Okay? So does bromine have 7 valence electrons? Yes, it does. It's in group 17. There you go. We can verify that. It's in group 17. It should have 7 valence electrons. The noble gas configuration tells you that it's 7 valence electron. And if you were to draw the Bohr model, here's real quick here. I'm just put the numbers 2. I'm sorry, wait, 2 here. 8, that's 10. 8 more, that's 18. That's many is that? 2, 8, 2, 8, 8, 18. 2 plus 8, 10. 10 plus 8 is 18. 18, that's 36. That's only 17. It should be 17 on the third energy level. And wait, this does not make sense. Take that back. This doesn't show the valence electron beyond element number 18. So okay, we can't use the Bohr model for the valence electron after the third row. But the Bohr model tells you that's the next energy level there. It's on row 4. On row 4 it has 17 electrons, and that is absolutely true. See, these are on row 4 here. This is on row 4. But it doesn't tell you valence electrons. So mark that out. Okay. So valence electrons, back to this periodic table, nice and handy here. The first column, by the column, you can tell which valence electron has what. Which column has which valence electrons, I mean. Column 1, 1 valence electron. Alkaline metals. Alkaline earth metals, 2 valence electrons. Boron group here, 3 valence electrons. Carbon group, 4 valence electrons. Nitrogen group, 5 valence electrons. And oxygen group, 6. Halogen, 7. Noble gases, helium have 2. Everything else have 8. Okay? And from electron configurations, add up all the S and the P of the highest energy level, and you have it. Same thing. Bohr model only works for the first 3 because it only goes up to 8. The other one tells you just how many is on that third row, fourth row, whatever row. But that's that. That's why Bohr's models changed to the orbital notations better. It tells us exactly how many with the S and the P's. Okay. So you should have this paper in front of you. Hydrogen. All right, put your name on that, period, date, valence electron Lewis dot structure. You need a periodic table. Okay. And the first thing here, first thing it's asking for is main energy level. It's saying basically what row is it on, the row number. Okay. Hydrogen is on row 1. Valence electron, how many does it have? It's in column 1. Remember, let's label our column so that we know 4, 5, 6, 7. Everything else here is 8, and this is 2. Okay. Sorry. There you go. Helium's 2. Everything else below that is 8. All right. So 1, 2, 3, 4, 5. We skip over the transition metals because they're different. Transition means they can change. That's why. Main energy level, the row is in row 1, so it's got, and then it's in column 1, so it has 1 valence electron. The Lewis structure, there are multiple ways of drawing Lewis structure, but the way that is acceptable to us now is just put dots around 4 sides. Okay, 4 sides meaning an element like hydrogen. It has 1 valence electron. You do that. Electrons will only go on these left, the cardinal direction, north, south, east, west. Okay, and for hydrogen, you draw 1 dot to represent that. And so to get a full shell, how many does hydrogen need to be a full shell? It's on the first row. It's in the first energy level. It only needs 2 to be full. Okay, so it can gain 1. Or if it loses 1, it can lose 1 as well, so that it goes down to nothing below it. So it loses that whole shell completely. Hydrogen will tend to do that. Hydrogen, it can lose an electron, or most of the time it will share, because we'll go over bonding later on, and because hydrogen is non-metal, it typically shares the electrons. Okay. Lithium, it's on main energy levels 2. How many valence electron? It's in the first column as well. So lithium's in the first column right there. So it's got 1 valence electron. So you write the symbol and you draw a dot. This dot could be on top, bottom, left, right. It doesn't matter. It could be like this. As long as there's 1 dot around there. Okay. It could be like this. Alright. Okay. That's that. So it's got 1 electron. It can gain 1. Now row 2, the second row, remember the second shell on the Bohr diagram, it can hold 8. Right? The first shell can hold 2. The second shell can hold 8. So, I'm sorry, it cannot gain 1. It's going to have to gain 7 to make a full shell now. But it can lose that 1 so they can have a full shell underneath. So here's what I mean by that. Here's lithium. There's 2 electrons here. 1 electron there. It can lose this entire shell out here. When it loses that one, then you end up with a full shell underneath. You can't see that anymore. It follows a full shell underneath. Okay, so and it needs a full shell in order for it to be stable. Okay, let's pick a more challenging one. Calcium. It is on row 4. Main energy levels. Energy level 4. How many valence electrons? It's in the second column here, right there. So it's got 2 valence electrons. So draw calcium like that. And when you have that, you pick a starting point, 1 dot, and you go left, right, top, or bottom. So you guys just go clockwise or counterclockwise. It doesn't matter. So that's calcium right there. 1, 2. And if it's got 2 to get to 8, now they all want to be 8. It can gain 6, or it can lose 2. Okay. What's going to happen is it's going to do whichever's easier. So like this first one, it's going to circle the one that is more likely going to happen. Okay. Lithium's, it's easier to lose 1 than gain 7. Atoms are pretty lazy. So whichever's easier, they will do. Calcium here, it's going to gain 6 or lose 2. Which one's easier? Which one sounds easier? Losing 2. Okay. If we go back to hydrogen, it's equally likely because you can gain 1 or lose 1. But that's hydrogen's a special case. Okay. And some here, lead, Pb. So if we go down to lead, is kind of, I want to pick one that's a little more different. The last one on here, phosphorus. Phosphorus is right there, element number 15. It's in column 5. It's on row 3, so energy level's 3. It's on row 15, so it's got 5 valence electrons. So for phosphorus, it's P here. You go 1, 2, 3, 4. There has to be 1 in each section before you can pair it up. So then the 5th one will be pairs. It will be paired with 1 of them. It doesn't matter where this pair is. You could easily start on top. If you start on the right, left, then that dot is on the left. Okay. There has to be 5 around there. It can only go in those 4 directions. Do not put it in like a circle like this. Like that is incorrect. Do not do that. Okay. So phosphorus here. I want to start at the bottom first. 1, 2, 3, 4. And there's a pair. Clearly there's a pair. There's a pair. And then we have 3 single electrons. 1 pair and 3 singles. So it's got 5. It can gain 3 to make to 8, or it can lose 5. Which one's easier? So this phosphorus will gain 3 electrons. Okay. And flip it to the back. I'm just showing you a couple examples so you can do the rest on your own. Okay. Case for helium. Look at helium right here. Symbol is He. Okay. It's on the first energy level. It's got 2 valence electrons. It's a noble gas. It's full. So to represent a full shell, we just keep them paired like that. This is the exception here for helium. It's full, so we keep them together. So, although sometimes you'll see helium looking like this. Some textbooks, some places will show it like that. But that just means that it doesn't look like it's a noble gas because it doesn't look full like that. Okay, when they're paired like this, we can kind of show that it's a full shell. it's a full first energy level, and it's a noble gas. Number gain, it doesn't need to gain anything because it's full. Number lost, it doesn't need to lose anything. So noble gas is not going to want to gain or lose. That is why they are unreactive. Okay, unreactive. Can't spell. Unreactive. Because they don't want to gain or they don't want to lose. Look at bromine. 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 Element number 35. Right there. It is in group 17. So it's going to have 7 valence electrons. 7 valence electrons. Main energy level. The main energy level, what row is it on? It is on row 4. Okay. Lewis structure, bromine, Br. So go 1, 2, 3, 4. Now start pairing. 5, 6, 7. There's 3 pairs and 1 single. How many more does it need to gain to get to 8? It needs to gain 1 more. If it wants to lose this whole shell, how many does it need to lose? It needs to lose 7. So which one is easier? It is easier to lose 1. You will realize after doing this for a while that non-metals over here, starting from column 5 here, will tend to will tend to gain electrons because they already have 5 or more. It's closer to 8. Okay. Non-metals on this side, column 3, 1, 2, will tend to lose an electron because it's easier for them to lose to get to 8. Okay. Complete these 2 worksheets, and I will show you the answers, or the substitute will give you the answers when she should have it. Okay. That'll conclude this video for today. Let's get it done, and it should be fairly simple. Goodbye.